Yeah, at least I managed it, but maybe we use the logon on ChatGPT tomorrow and not today because it has lasted half an hour because I think 3 or 4 times I had to identify myself. Okay, we started last week with this general problem. Maybe I copy this again that we can even see something. What we, oops, wanted to do. This one, this one, this one, and this one. The rest we delete. Yeah, so our task was that we in general assumed that the central bank has two targets and that we have a trade-off between these two targets. So on the one part, our task at the central bank is the target of price level stability, and this means we have a focus on inflation, and in general from the ECB, you even know from a protocol in 2019, I think, no, not 2019, it was 2021. There we really focused that we want to keep inflation at 2% in the medium term. Well, we simplified this here that we said, let's say that our target is 0% inflation. Qualitatively, of course, this doesn't matter. We just have to have one target. And also, we focused on the general performance. We focus on the general performance of our economy. And for this, we look, so to speak, in the medium term or long term on GDP. And for this, since it is the long run perspective on potential output, so we want to keep the economy around the potential output and Y star. And there we also then assumed that we want to push in general output a little bit more than these potential output Y stars. So we multiply this with a number K, which is larger than 0, larger than 1. And yeah, why do we have a trade-off? Well, about this we have generally spoken. This is due to the Phillips curve that if, and here we used the expectation augmented Phillips curve, that we say that we have a positive dependence between output and inflation if inflation are above expected inflation. So this is larger than 0 if the actual inflation is larger than the expected inflation. Well, and now we more or less can forget about what we have talked what is the problem in a macroeconomic perspective. Now we just, this I forgot, and we defined our losses as the sum of the squared deviations from our two targets, 0 inflation and K times potential output. And where does that loss function comes from? Well, you also can in general compare this when you have defined in statistics standard deviation or volatility variance. This is also the sum of the deviations, the squared deviations from some average. Yeah, but then when we have formulated this, this is just a minimization problem subject to some specific condition. And then if we look at these at this problem, we generally see, well, here we have a function depending on two variables. This is a condition where we have one variable is depending on the other. And since our functions quite simple, so here we directly have the dependence and not an implicit dependence between these two variables. We just can formally feed in our condition in our target function, in our loss function, and then we obtain a function L of pi, comma, y of pi, and thus in the end this function is only depending on one variable. And in order to optimize this, and this would be then the substitution method, and this we have done last week, we just can calculate L prime to be 0. But then from this method we are not done, since we still have within our Phillips curve the variable of expected inflation. So from this we obtain a so-called reaction function that optimal inflation set by the central bank is depending on expected inflation. This is the reaction function. Well, and due to this dependence of where want I to put inflation as the central bank in an optimal way, I also have to make assumptions about how the public is forming these expected inflations. And there we have assumed three different setups, and we had calculated the so-called discretionary part here, and for this we assumed, well, that the public knows that the inflation target is 0, but since also the public knows the general loss function of the central bank and that they want to minimize these losses, they also can anticipate this reaction function of the central bank. And then we assume rational expectations that the public assumes the central bank is reacting due to its reaction function and is therefore setting the inflation rate with respect to this reaction function, and then we obtain this equilibrium condition that expected inflation has to be, due to our assumptions, the actual inflation rate, which is set by the central bank. So this is the equilibrium condition. And I think that it was what we have done last week, that in the end, let's see if I can find it, that we have in the end pi star as our equilibrium inflation rate. And let me rewrite it, that this is B over A times K minus 1 times Y star. Well, and with this example, I also want to show you other concepts which you have already seen in your studies, especially in my course in macroeconomics and also I think in microeconomics, that if we have such an optimization problem, we also can use other methods to solve this problem. And since we have in general here a minimization problem subject to some conditions, we can also use the so-called method of Lagrangian multipliers. And this I ask you, that maybe you had already a look at this for this week. Well, multiplier method, then we use a method which is quite often used in mathematics, and this means multiply some functions with a special one or adding some function with a special zero. And the second one we use here, that we define our Lagrangian function as to be our loss function. This was 1/2 times a pi squared plus y minus ky star squared. And now we are adding our special zero, that we say plus lambda Lagrangian multiplier. And now we rearrange our condition in a way that this will be zero. So we just subtract the right-hand side. Y minus y star minus b times pi minus expected inflation. And this is just zero. And then we obtain a function which is depending now on three variables: pi, y, and our new introduced variable lambda, the Lagrangian multiplier. This we want to optimize now, because now we have incorporated into our target function our condition, because we have a conditional optimization problem. Somehow we have to feed it in. In the first method, we just feed it in directly. But this is not always possible if you have more complicated conditions. Then maybe the dependence between the variables is only implicitly given. And this means you cannot solve to y depending on pi. think of there is some exponential dependence. Then quite often you cannot solve this condition. And well, but if we have a function depending on three variables and we want to optimize this again means just that we have to take all three partial derivatives and to set them just to 0. So this would be then dl d pi then here we have our inflation, and from the first part we just obtain again a times pi, and we have here pi, and then you see here is no dependence, so we are just left taking the derivative of lambda times b times pi with respect to pi. So this means minus lambda b. Okay? Oh, I'm awfully sorry. I haven't. I haven't. Yep. Shared the screen. In this case, you can just mention this. Anyway. And this has to be 0. And now we are taking the derivative of our Lagrangian function with respect to the second variable with respect to y. Again, here we have the dependence. Taking the derivative of squared means again 2 in front of our brackets. This is canceling with our factor 1/2 here. So we end up with y minus k times y star. And now we have here our dependence, and we then get plus lambda equals 0. Well, and the last derivative is just our condition, our Phillips curve, because this is the way how we constructed it. Y minus y star minus b pi. Yeah. And now we have three we have three conditions and three variables, and this means now we want to solve for our three variables, and this is what you very often can do in economics if you have this Lagrangian method, that you just solve the first two, that you write down pi equals lambda b and y minus k y star equals minus lambda. And if we divide now these two conditions through each other, the left-hand side, the right-hand side, then you see that directly the lambda is canceling. So we obtain a pi over y minus k y star equals minus b, and thus we obtain pi equals minus b over a times y minus k y star. And now we want to get rid of our y. So from this, we again rewrite it to our general dependence of the Phillips curve y star plus b pi minus pi e. We put this into our condition here. Let's say this is 3, and then this with 3 means that we obtain minus b over a times y star plus b pi minus b pi e, and that it minus k y star. This we can rewrite to b squared over a, and now I use this one at first. So we have minus, and minus is plus times expected inflation. Then I take this one here. So minus b squared over a times pi, and these two terms with y star I also take together, and I obtain then plus, and now I turn it around. I have here a minus sign. I have here a minus sign. Minus is plus, so plus k, and in front of our y star here I have a 1, but minus times 1 is minus 1, so I obtain here k minus 1 y star. This is pi. I want to solve for pi, so I add the term on the right hand side with inflation, and then I obtain pi times up. Is there something still missing? What is missing? I missed a here. There has to be an a, and there has to be an a. So I obtain then a plus b squared over a equals b squared over a times p e plus k minus 1 y star. Hopefully now I have done this in the right way. There is still something wrong, I think. Up. This factor is not wrong. It's not right. This has to be only, oops, I have this a, so it's a plus b squared over a. And let's see, in the end I have to reach the same result as here. So hopefully I end up with the same reaction function. Let's see if I make it. There is something. Is it right or not? Or if I missed something here? Hmm? Pardon. A plus b squared. Something is wrong at this point. Uh, oh, sorry. This a is wrong, or because I divided here by a. So again, this, 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 and then I obtain a 1 here. This seems better, yeah. So this is a plus b squared over a. And now I multiply both sides with the inverse of this factor, and I obtain pi equals a over a plus b squared times b squared over a times pe plus a over a plus b squared times k minus 1 times y star. This cancels, and in the end I get b squared over a plus b squared expected inflation plus a over a plus b squared k minus 1 y star, and this is again my reaction function, and hopefully this is now the same one as last week. Here b squared over a plus b and b k minus 1 over a plus b squared. This seems to be the same. Um, is this the same? Did I again missed something? Uh, the factor in front of this. Here again I missed something. And what did I miss? I missed this factor has to be also in front of our output target because it's a bracket. Do you see this? So this is also multiplied with this part and with this part. So it is then here b over a, b over a, and b over a, and then this and this cancels. And now we have this here. And now both functions on the former slide and this slide are the same. Well, and hopefully you recognize that technically it's the same as you have done it in micro or in macro when we have also calculated in my course, it was the calculation of the labor supply. So compare this. Compare with micro utility max or macro labor supply. And there you had a function L, and let's specify. I think you have maybe used L is x1 times x2 plus lambda m minus pi1 x1 minus pi2 x2, which was just a function depending on x1, x2, and lambda. Do you remember this? And then the technical procedure was the same, taking the derivative with respect to x1, x2, and lambda, and then putting these equations into each other in order to solve for the optimal demands depending on prices and income. So, and then the last one, total differential, or let's use another slide, a new one. And let's copy the loss function and the other one here. So this one, oops. How did I get my function? So, and these two. Well, graphically from micro, this max u subject to m equals expenditure, you have done the following. x2 x1. Then you set some indifference curve, setting utility to be constant. And then taking the slope of your budget line and where the two slopes coincide, this was your household optimum. So, and now we are doing the same. Set u equals u bar. Now we are doing the same and we just set our losses to some constant. So set L equals L bar and calculating the total differential. So if L is a constant, then the change of a constant is just zero. The derivative of a constant is zero. So we obtain then 0 is, and here we have again this dependence on our two variables, pi and y. So what we have already done, we are taking the derivatives with respect to our two variables. Here we can just have a look at the former slide. So we obtain a times pi, and now we are varying this inflation rate, so times d pi, the differential of the inflation. Of inflation plus the derivative with respect to y, and this was just y times dy, the differential of output. Well, and this now we can solve for the slope of here our indifference curve and here our, so to speak, constant loss curve. This would be also an indifference curve. When are losses not changing? So then we can solve this, that we have dy over d pi equals minus where do we have it? So I have to divide by y. So this is a pi over y. And what is the slope of the Phillips curve of our condition? Here, the slope of the budget line was just minus pi 1 over pi 2, if you remember this. Slope of the budget line. Here we just calculate the slope of our condition, which is the Phillips curve, and the slope is just b with respect to pi. This is just b. Well, and how does this now looks like? Well, if we put this into a diagram, y depending on pi. So what kind of curve is this? How does it look like? Well, we have here just, and setting this to a constant, we have more or less one variable squared plus another variable squared is some constant. So this is then in general something where we could say z squared some constant. This is just some constant number. This would be our L bar equals x squared. This would be then roughly our pi squared plus y squared. Well, this would be then roughly our y minus k y star squared here. An a is missing. Okay. And from school, do you remember what kind of figure this is? Or do you remember something from school where you have a squared plus b squared equals c squared? So this is then just your rectangular triangle, A, B, and C. And from this, yes, this is the Pythagorean theorem, that the sum of these two small squares equals the large squares. Well, and then I think in class 9 or 10, you introduced the following. Yx, that you had a circle, and then you said, well, if I have here an angle, and I go down here, that this here, and this would be the angle alpha, that this would be the cosine of alpha, and this would be the sine of alpha. Well, but this is also just a rectangular triangle. And from this, you have the so-called addition theorem for cosine and sine, which would be cosine alpha squared plus sine alpha squared equals 1. So our loss function more or less looks just like this. So if the square of the sum of the square of two variables equals a constant number, here the constant is 1, but this of course could be 4, then you would have a larger circle. So our L bar is just the radius of our circle. So our loss function more or less represent just a circle, but the midpoint is not the origin, here we start, or our target is zero inflation. Okay, this would be then zero for inflation, but our target here is a little bit shifted upward to k times y star. So then we end up here with the midpoint of our circle at ky star. And then we have to draw just a circle around this midpoint with our with a radius of L bar, which is just a constant. Well, and then we have to admit it is not a circle because we have here in front of pi, we have also a weight, and this could be any positive number. And this then would mean that we do not have a circle, but we have an ellipsoid. But let's, for simplicity, just draw this circle. So this circle then would be the same as, or not the same, would be then our indifference curve from microeconomics. And our condition is also just a straight line. But here in microeconomics, it was a falling straight line because the slope was minus. Now we have an increasing straight line with a slope of plus b. So our optimal point would then be somewhere where the two slopes b and the slope of our constant loss curve, indifference curve, will coincide. So this would be then our optimal inflation. Well, and let's see, hopefully all my calculations are right. Now we match these two slopes. So we have minus a times pi over y equals b, and then we obtain pi is minus b over a times y, and hopefully this we have also here. It is where it is. I miscalculated something here. Yes, here it is. Again, a mistake. I have the outer derivative. It's the square is around the bracket. So this has to be y minus k y star. And so I also obtain here y minus k y star. And then I obtain here y minus k y star. Sorry for this again, but I do not want just doing this calculation and just looking at my sheets of paper, because then hopefully you also see that you have really to be careful to grow through these calculations. And you see I'm also doing mistakes. So, but then if we go to this one, we have that this condition here is, of course, the same as this condition here. And all the other calculations which we then have done are, of course, the same ones as we have done it before. So this then means in the end we get this condition for the reaction function. Yep. Is it possible? No, that is not possible. Oh. Uh, and now I can move this down here. So, and then these are the three different methods how you can solve such an optimizing process. Now I'm running out of time because the next step will then be that we compare these three different concepts of forming our expectations. So what we have now only done is using the reaction function, the discretionary concept, but using then the reaction function, we can use the second one of deception and commitment. And in the end, then we want to compare the outcome of these three different setups of forming our expectations, and especially to compare the losses between these three different setups. Okay, but we have our career day today, which has already started at 9 o'clock, and maybe you will participate there. Okay, then thank you very much for today, and hopefully you have seen that we have used the concepts you used in other lectures, because these are the very general concepts to solve optimization problems. And economics is very, very often about optimizing.